Today I'd like to share you some scientific things that I recently discovered with God's help, and I'd like to present it to you. It's about the quantum mechanical origin of gravitation. In this theory, I try to explain that gravity, or I try to show people that gravity has a direct quantum mechanical origin. And for that I like to show you on the board. That's why the board is standing over there. Okay, so I'm going to start. You will not see me that much in the picture, but the more the board. Okay, now, as it most probably turns out to be, is that Heisenberg, the uncertainty principle of Heisenberg, I have to take a good pen, of course. I didn't test them. Sorry for that. Yeah. Heisenberg's uncertainty principle. Now it's by the way, it's kind of warm here. It's in the summer of 2020, and it's pretty hot here in so I keep it as short as I can because it's hot. It's warm. Okay, the Heisenberg says this: delta T delta E is bigger or equal to h about divided by 4 pi, and delta x, delta p, delta x, not the other way around, delta p is bigger than h over 4 pi. Okay, we know that this is true. Now, what you can do is you can write this delta t and delta e is mc squared. So you have mc squared. Now c is a constant, so you can bring that to the other side. 4 pi c squared here, c squared there. Okay, and here delta x, delta p is the p is m times v. Now delta m v, bigger than h 4 pi. Yeah. Now what you see is that in both cases we have a mass here. Yeah. The thing is, let's take a big mass, Mbig, like a planet, like etc., and a small test mass, mt, and test. Now what you will see is that this is consistent of protons and electrons. And they have got fixed masses, so the masses of protons and electrons, all combinations are, and the planet is neutral, so there's no charge. That means that there is a combination of proton and electrons altogether, and they have fixed masses. Even a neutron is a combination of a proton and an electron. So this mass of this object, especially from a close range, a small r, it's pretty accurate to sense, to detect, even for a particle, but also for a measurement, an instrument. If you're close by, you can easily determine the mass. So that means that the delta mass, delta t, delta m, that delta m, this is very small. This has a limit to delta m going to 0. Not 0. But that means that the delta t must be growing. It's growing up. So it becomes a delta t. Now that happens in this atmosphere, in this here, that the delta t due to that the mass is pretty accurate to be determined, then you have a high insecurity, a blurring of delta t. Well, that's the part in which the time dilatation occurs. Yeah? So because you get, instead of a very small time difference, you end up with a very large time difference, a very blurriness of time, so to say. And that's exactly also what Einstein says. I mean, Einstein says that the time and the space is warped, is bent, is altered. It's not normal as in empty space. And that's what you see here. So a big mass, which is pretty accurate to measure. I mean, we can determine the mass of the Earth, pretty accurate, and even the Sun and also the other planets. We can determine it pretty accurate. So, but that means that the insecurity or uncertainty in time is pretty big, and that's where the time dilatation comes from. Okay, if you go further away, yeah, then I mean, if you go further and further away from a massive object like a planet or a star, then it's harder to determine the mass. So the mass, the delta mass, is becoming bigger, due to which the time dilatation is shrinking. So dt becomes dt. Yeah? As far in open space and far away from an object, I mean, it's very hard to determine all kinds of masses from stars far, so many millions or billion light years away. That's very hard to determine. And the bigger the distance, the harder it is to determine the mass of it. That also means that the time at our position for measuring that object, or our sensing, the ability to measure it, there is little uncertainty or blurring of the time. That means that the delta t is going to dt, to zero, to smaller and smaller ranges. So that's why time is less dilated. Okay. The same thing occurs here with the position. You see here the combination of the space, delta x, and delta mv. Now, as we told before, delta m is becoming, if you're close by, if you're very distant, close by a big mass, then delta m, indeed, as here, becomes dm, dus very small. It goes to zero. Yeah, or the uncertainty is becoming smaller and smaller and smaller if you are close to an object. That's why the space uncertainty enlarges, and that is the stretching of space. Now, the combination of in both cases, if dm goes to zero or is getting smaller and smaller and smaller, like I told you here, then both dt and dx becomes bigger and bigger and bigger. And that is actually the warping that Einstein discovered in his, the warping of space-time. And that is this. And so that's basically the discovery. And I wrote a paper about it. I will put it down in the description where you can find that paper. I must say it's not entirely finished yet. I'm working on it. But the main lines, the main thought is published already, so you can read it already. What a little bit of the mathematics behind it is, but I tell you again, it's not finished yet. You can find it at ResearchGate. You can find it at academia.edu. Both I put the paper over there. But this is in short the idea of where space-time. Oh, wait, you didn't see it here, right? I wrote this here. So in short, I put it again. The delta m becomes closer to zero, so also the delta x must enlarge. Here the delta x, you get delta x p, in which p is m times v, and where the delta m becomes smaller, so the delta x becomes larger. And this is the space-time warping of which Einstein showed us that space and time are being warped, are being bent, are being changed. And this is actually the whole idea about space-time warping, bending. So Heisenberg, the Heisenberg uncertainty principle, is the direct cause of what we know as gravity. And especially if you look at black holes. Black holes is a very big mass. From close by you can determine it pretty accurate. And if you and so the time dilatation must be gigantic according to Heisenberg, but also according to Einstein. And the further away you go away from a black hole, the harder it is to measure the mass of that object, of the black hole object. So the smaller the time dilatation becomes. And the thing is also that the same goes for the space parameter. And that the uncertainty in mass, if you're closer by, you can measure it more accurately. The uncertainty in the masses gets smaller and smaller if you go closer to a black hole, but the spacing uncertainty grows larger and larger and larger, and that's the space-time warping of which Einstein predicted and showed us that gravity is nothing but a space-time warping. Einstein said, well, mass is telling space how to bend, and space is telling mass how to move. And that's basically correct, but the fundamental origin, the fundamental mechanism behind it is, as shown here in very short, is the Heisenberg uncertainty principle. And the thing is, what I want to mention is that I showed you also in another paper, and it's called STEAM, space, time, energy, and mass idea of theory, is that space, delta x, time, delta t, energy, delta E, and mass, delta m or PV in this case, no P, is P, which is mv, Yeah. That is very closely related. I wrote a paper also about the conservation of space-time, energy, and matter. You cannot change one without the other. If there is a mass and thus energy, then space and time must be altered. If space and time is altered, then also the mass or the energy close by must be altered. So there is a very tight correlation between these four parameters, space, time, energy, and mass. You cannot change one without the other. And that's why I called it a conservation principle. And also with the speed of, if you speed it up, if you speed a mass up, then the mass increases, then the time slows down, then the dimension shrinks in the direction that it's going, and so on. So if you change one of these parameters like speed, or you drain down the energy, then and you slow it down, then the energy gets lower, then the dimension is enlarging again, then the time starts to run in a normal phase. So you cannot change one without the other. So therefore there is a conservation principle at work in speeding up and in slowing down and so on. But also that means in masses, in gravity. And that's why the whole Heisenberg uncertainty principle comes around the corner. Where this mechanism plays a key role in acting or creating, emerge the gravity. So because the mass the uncertainty in mass is getting smaller, then the uncertainty in time spans or the time is getting more blurrier. You have a bigger time span in which things can happen, and you have a bigger spacing, uncertainty in spacing. And that's where the whole space-time bending, warping comes from, which Einstein predicted in his theory. So okay, this is what I want to share. I keep it short because it's pretty hot right now, and I'm going to take a nice shower because it's hot. I want to cool down, get a swim or something like that. Okay, thanks for watching. See you next time. Hasta la vista.